Hey everyone, so my name is Matt Morgan. I work here at Uber. I'm on the web platform team, leading that team, building sort of our underlying web architecture. And this is our second meetup. This is a meetup that we put on to bring both outside outside speakers as well as internal speakers from Uber to talk about building high quality web applications. So today we have some awesome speakers. We've got Ariya Hidayat, Sean He from Uber, and then we also have Guillermo Rausch from Zeit. So without further ado, let's have Ariya come up and talk about squeezing images.
Good evening, everyone. I'm lucky tonight there's no Warriors game, otherwise it's going to be hard to compete with the game. So thank you for being here with me. As I prepared the slide deck, I was looking for the pictures of some cats following the internet tradition. Right? So I launched my Google Photos apps and searched for cats. Unfortunately, nothing was there. So I was a bit confused. I remember I took some picture of cats. Maybe Google algorithm is not that good. So I decided, what about big cats? What about some tigers? So that's what I did next. And the search outcome is really surprising. So among others, it found the pictures of my daughter from years ago as she finished with some face painting session. And there she is, right, her face and others, resembling a tiger. So now I think Google algorithm is pretty good. I don't know whether I should be terrified or happy about this. With that, so this picture of tiger is going to be the example pictures I'm going to use throughout the slide deck, and probably the most adorable tiger that you've seen for a while. Tonight we're going to talk about squeezing images, specifically about PNG and JPEG, and the focus here solely about those two image formats. We're not going to talk about how to switch between, how to choose the right format, whether to use raster or vector, why we should use raster images instead of SVG. The focus is solely on the PNG and JPEG. Just like many talk about web performance, I think we should set a new standard. When we talk about optimization, we should carefully define what we want to optimize for. Because optimization is nothing but trade-offs. Sometimes we just throw the terms web performance, web optimization without carefully defining what kind of trade-off we're going to have. As with kind of trade-off, you can have fast, good, cheap, pick two, not all three. For this particular discussion, we're trying to focus on two particular constraints. If you have an array of colors in the form of images and you want to deliver it to the receiving end, how do we do that in such a way that the size is the smallest, but at the same time we continue to maintain the quality? So there are two very important constraints here. Number one is the size, and the second is the quality. Now, if you don't care about one constraint, it's very easy. If you don't care about the size, then you can just send the highest quality possible. Then you maintain the second constraint. If you don't care about the quality, then you can just compress it as small as possible, even if it's blurry or even if it's not clear. Now, as with any other technique of web performance and optimization, we try to hit this both constraints in such a way that it will fulfill the requirement. How do we do that? Let's say we draw this quadrant, because I love quadrants. Gartner generated millions of dollars just by inventing quadrants, so trying to steal that trick. If we have file size here and we have quality, so this is our original image. The size is big because you probably just snap it from your phones or cameras. And then the visual quality, of course, the best that you can get because it's fresh from all the pixels. This is not acceptable. Yes, I can reduce quality while maintaining the size. You never want to go there because there's no point there. The size is still big, the quality is terrible. What we want to achieve is this one. This is the best possible that ever happened to us because the quality remains the same, but the size just dramatically decreases. In the real world, it's not possible to do this. So what we aim is somewhere in between where it's a bit more optimal. Yes, we reduce the file dramatically, but at the same time, hopefully, we just decrease the quality just a little bit that none of us will notice it. So that's the goal. And we're going to explore some techniques in order to achieve that. Before we go there, let's mention a little bit about encoding and decoding. So if you have pixels full of colors with the encoding of process is going to be turned into a series of values. In this case, it's binary numbers. And then the decoding format is responsible to turn it into color values in form of pixels or images. We're going to see a couple of important encoding and decoding techniques. There's also two types of both encoding and encoding, lossless and lossy. Lossless means if I turn these images into a series of values and I turn it back into colors, then the new result is completely identical to the original. Slightly different in the case of lossy, because the outcome might be slightly different than the original. And we're gonna try to take advantage of that. There's also many different types of encoding and decoding. For instance, when I took that picture from the phone, it's 8 megapixels. And when I check the quality, it's set to 95, the JPEG quality. And the file is just about 2 megabytes. When I use JPEG encoders, such as most JPEG, it takes 2 seconds to turn it into a different image with lower quality. And the file size is just 900 kilobyte or so. But there's also different type of encoder, such as Guetzli from Google, which take 5 minutes to produce the JPEG file. And the outcome is roughly the same. So we're gonna see why this is different and what can we learn from all these different type of encoders. Now, without further ado, let's talk about JPEG first. The biggest technique in JPEG compression is to split it into multiple channels. We know about the color format red, green, blue. That's not how it works in JPEG. So in JPEG, the image is split, or the color is split into 3 channels. And there are 2 for chroma and 1 for luminance. Luminance here, in layman's terms, is almost representing the intensity. If you remember the old black and white television, this is what is being sent, even though the transmitter is color transmission, so that all the black and white television can still see the images. The idea is very simple. Our eyes are so sensitive to the intensity. That's the amount of information that needs to be preserved the most. If you look at this, if you look at the other 2 channels, you can hardly see the face and the structure of the images. But if you just focus on this, it's clear. This is the image of my daughter being face painted. Now, the idea is that JPEG will split all those images into blocks of 64 pixels. It's a square of 8 by 8. So your image will be split into blocks, 1 by 1. And we can start to see the pattern where all the values here on those 8 by 8 blocks, they're roughly the same. They're not completely identical, but they're almost the same. This is the typical value, the typical pixel values that you get when you take pictures of, for instance, the nature or some face or anything that doesn't resemble logos or drawings. The next step from taking these blocks is to convert it from the pixel values to the frequency domain. Without going to the math, what it does is basically turning one values into another. What is important here is that this represents the frequency distribution. This is similar to if you're into audio, then you have the equalizer where you can filter certain frequency. This is just the first step, the discrete cosine transform. We got a bunch of values there. The next step is to start to quantify the values. As I mentioned earlier, we can sacrifice some values. In the case of JPEG compression, we can emphasize certain values. The best way to experiment with the values is to use Photoshop or any other image editor and then save the original image with different Q. And then you can start to see that if the Q is very low, things are mostly blurry. And if the Q is very high, you can still preserve all the details. In other words, the high Q preserves the details, low Q sacrifices the details. How does it do that? So the Q is basically being used to quantize all the values in the original the DCT values that I shown before in the slide deck, and then turn it into something that resembles on the matrix on the right side. This is important because once you do this, suddenly the values on the right sides are mostly zeros. There are some big numbers over there, big integers, but mostly they're zeros. And this leads to much better representation of the values as it's being compressed by JPEG. There are more resources along some of this. In some of the slide deck, I put the link there so you can follow that at your own time to see more details about, among others, the Q factor. Now, how do we play with this? How do we take advantage of different Q factors? It's very easy. You can use various JPEG encoder. One of my favorite is the one from Mozilla, MozJPEG. This is a modification of the original JPEG encoder, the official one, modified by the Mozilla folks to optimize for it. You can use the command line tool, see JPEG, and then pass the quality, and then get the original file, and then it's going to output a new file with a different quality. This is how I get to the file size of only 900 kilobyte, whereas the original image is 2 megabyte. You can also use the one that I mentioned earlier, the new JPEG encoder from Google called Guetzli. Works the same way. It's a command line. You pass the input file, it gets the produce the output file with the specified quality. Now, as you can see, even if I pass the same quality, the file size is roughly the same. So what's the difference between MozJPEG and Guetzli? The difference is the so-called the psychovisual similarity. There are many different ways to quantify whether one image is similar to the other. There's SSIM, structural similarity. The one that is used by Google is called psychovisual similarity. It's a different project called Butter-Augli. Basically, if you pass two images to this command line tool, it's going to produce a number. In this case, 2.3 or 1.9. The number doesn't mean anything. It's very abstract. There's no correlation with the physical quantity. The idea if the image are completely identical, then I think the number should be 1 or very close to 1. And if the number is big, it means that the images are not the same. And this simulates how we perceive that. There's many different models. This is one of them. As you can see, although Guetzli produce roughly 900 kilobyte images, but if you match it to the this psychovisual similarity, it produces a lower score, which means the outcome is less perceivable from the different perspective to the original image. Whereas in the case of MozJPEG, yes, the output file size is also 900 or 800 kilobyte, but in theory or in practice, people will start to notice more differences between these images. Now, as I mentioned, the price that you pay for doing Guetzli is that it takes ages to do that. It takes 5 minutes. If you re-encode a JPEG image using MozJPEG, in a fraction of seconds, you get the new output. Does it matter? Yes, of course. If Guetzli is implemented in a digital camera, then nobody will want to use that because you snap a picture and then you can't do anything until the camera finishes encoding all the JPEG, 5 minutes or so. That's not fun. But if you want to serve a JPEG, the web server, the rest of the world, or you want to share a picture with some of the folks, then this one-shot process of 5 minutes is totally worth it, because not only everyone will enjoy high quality, the file size potentially could decrease as well. So that's the trade-off that we need to hit. As I mentioned earlier, JPEG compression works by eliminating details. So one way to eliminate details is to apply blur. Obviously, you cannot apply blur to the entire things because then everything will be blurry. But you can start to be selective with respect to parts of the pictures that you want to blur. For instance, in this picture, I can take this picture on the left and then select the background and blur it just a little bit. And then use the JPEG encoder to start to produce different image. As you can see, I have a saving of about 10% just by blurring the background. Of course, it doesn't always work. So it works only in some cases. And when it works, when the opportunity presents itself, you should definitely take advantage of that. Now, if you use Pixel 2 or iPhone X, then you have the so-called portrait mode. This is extremely advantageous because if you see this picture, this is the one taken without portrait mode, and this is the one with portrait mode. The idea is that it just blurs the background. Not only the picture looks more professional, I've got a lot of compliments from that kind of pictures, but the size is also massively different, right? This is barely 2 megs, and this one is almost 3. So the size is 75% of the original. And this is just the original. I haven't done, I haven't tried to re-encode it using either MozJPEG or Guetzli. So if you have portrait mode in your phones, then try to take advantage of that. Not only the looks is fantastic and you get a lot of compliments, the size is also small. So that's about JPEG. Let's talk about PNG or PNG.
JPEG works by converting the image from spatial domain to frequency, remove all the high frequency, thereby removing all the details, re-encode it efficiently, and then the outcome is a bit lossy. You don't get the same pixel as the original pixels.
Now, it doesn't work for logos or drawings or clip arts because you really want all the details. Right? If your corporate color is green, you want the outcome to be really green, not some greenish value. Right? For that, PNG is the perfect format. There's many different style of color encoding for PNG. It's all described in our RFC 2083. The typical one is the true colors, but we also have index color. If the total number of colors in the picture is less than certain numbers, then it doesn't need to use the RGB channel for that. Or grayscale, if you use a grayscale picture, then there's a specific encoding for that. But let's focus on true color. What it does is to split the image into red, green, and blue, and encode each color or color channel using the so-called DEFLATE, and then optimize it further using Huffman compressions. So DEFLATE is basically a combination of Lempel-Ziff and Hoffman. Hoffman is very old. The paper is from 1950. Lempel-Ziff is from 1977. DEFLATE is very powerful. What it does is to detect sequences, repeated sequences, and try to encode it efficiently. The best way to explain this is by using the help of Taylor Swift. Any Taylor Swift fan in the house? So if you see one of the song, typical song from Taylor Swift, right? So, because the player's gonna play, and then we can see there's a lot of repetition there. Instead of repeating every single letters, every single words, what DEFLATE will do is to detect all the sequences. For instance, well, there are 1, 2, 3, 4, 5 letters there, space, P-L-A-Y, that have appeared before, just a couple of letters before that. So why do we need to encode the entire characters? We don't. So DEFLATE will replace it with a magic token, 514, which indicates that take 5 letters, 14 characters before, and then just duplicate it. You don't need to repeat the entire 5 characters a lot. The same thing, the next one is even better because there's a space, P-L-A-Y, and comma, and that's 6. So you don't need to repeat that. All we need to do is use a special magic token to indicate, go back 6 characters and copy the entire thing. And if you do that, then hold on. If you do that, then we can encode this entire line very efficiently. We don't need to repeat the wordplay multiple times. The repetition even happens in for a tweet, right? One time I tweet about this. This is your annual reminder that Java is to JavaScript as horse is horseradish. There's a lot of repetition there. Java, JavaScript, horseradish. As a non-native speaker, I'm always confused by the word horseradish, right? It's neither a horse nor radish. I don't know. How can you come up with that word? If you use DEFLATE on this, then you can see that there's a space Java that can be repeated or encoded more efficiently. There's a horse there from horseradish versus horse, so you can save some space. Now, how does it work in PNG? We detect repetition, and repetition happens in the form of color patterns. So if you take the picture of this different tiger, and then you zoom in, then you can see there's a lot of color bands there. There's black colors and orange and so on and so forth, right? So what it does is to apply DEFLATE on those series of colors. But in order to do that, first we need to split it into 3 channels, so red, green, blue, and then each channel will be applied to the DEFLATE compression algorithm to find all these repeated colors and encode it more efficiently. So PNG compression is all about series of similar colors along the horizontal axis, and in some cases you can view the efficiency as a form of how many same colors you have in the pictures. Right? There's a tool that allows you to see, given an image, what are the parts that can be compressed efficiently and what are the parts that cannot be compressed efficiently. Now, if you pay attention to what I said, where same set of colors will be compressed efficiently, it means that along the edges they won't be compressed efficiently. And that's what we expect. There's also the search of duplication, right? Yes, you can search for duplicated patterns, but how much you want to search it, how farther behind you want to find all the duplication. This is an example again. So I can do this 514, 6, 6, 6, 6, 6, 6, 6, 6, which means I'm just going to repeat 6 characters because it appears before. But I can also do this. I don't need to repeat 6 characters at once. At some point, there's 12 characters that have appeared before. So if I do this, it will be encoded more efficiently. But this is going to take some effort because I have to try a different exhaustive combination to find the smallest possible encoding. So now there's a trade-off. Even if there's a similar color along your PNG image, the encoder needs to find well, do I need to find every possible combination, or do I need to go back very far away, or am I satisfied with just looking at the neighborhood pixels values? So that's the optimization. There's a PNG encoder from Google called Zopfli. Zopfli works differently than typical PNG encoder. This encoder tries very, very hard to find every single similar color patterns throughout the images so that the output could be the smallest. The output can be extremely efficient. As you can see here, if I apply this to some sample image, then the outcome is going to be 68% smaller, or the output file size will be 68% of the original. And that's the same image. So I don't lose anything. I don't lose any pixel values. PNG is a lossless compression. After this, the Tiger Small is exactly like Tiger. People will not notice the difference. You have to pay attention for this because in PNG format, there's also color space and color information. So if you want to preserve the same exact RGB values, you might want to also pay attention to those chunks. But in 99% of the use cases, if you just run Zopfli on your image, PNG, you can get the smaller file with zero quality degradation. The file is just smaller. It's going to take some time to run that, but like I mentioned before, if you serve some files on the web server, it's totally worth it. Because if your website is extremely popular, imagine those million visitors who need to download the same large PNG all the time, whereas we can have saving like this, right? So this is also much more environment friendly. You reduce the bandwidth for everyone. This is the compression, the difference in the file size reduction. Now, what are the techniques that we can use? Similar to JPEG compression before, well, what if we can sacrifice some details? In this Tiger image, we have 9,734 distinct colors. What if I can just reduce it only to 256? Well, it works because in some cases, you don't really care about so many thousand or bajillion different colors. As long as it looks roughly the same, well, we can live with that, right? So here's the demonstration. Here's all the full colors, and this is the reduced one. Can anyone notice any missing pixels? Of course, it's right there. I know that. Which part? Only if I superimpose it and then do a diff through the pixel, then you can start to know, right? Oh, those are different than this and that. So there are many different techniques to reduce or to quantify millions and thousands of colors into just a small set of colors. And since it's a small set of colors, you need to sacrifice some parts. Unless you do it very inefficiently, usually we won't notice it. Human beings won't notice missing RGB value in some pixels. So if this is something that you can live with, why do we need to use this? So if you can sacrifice some details, do that. And there's a tool called PNG Quant that could do that. You pass the image, and then it will produce another image, and then you specify how much colors I want in this image. If your image is just screenshots for your blog or something like that, people won't care about missing values. If it's a tutorial for Photoshop, sure, you have to preserve all the color values. But most of the time, screenshots for blogs and for articles and such, there's no need to preserve all the distinct colors. Thus, just pass it to this tool. It does a lot of work to make sure that all the color choices, the selection of those colors are optimal. But this is one time. Once you do this, you can just forget it. And then you can reduce the color even further. So the Tiger that has been reduced to roughly 130 something can be even smaller after I choose to sacrifice some colors. So do those two things, sacrifice some colors, sacrifice some details, and then use an exhaustive encoder. So that's basically what it's all about. I really want to emphasize that we sometimes need to understand how the tool works. We cannot just use any kind of web performance tool, image optimization tool that someone recommend to us. We really need to understand how it works, because only that way we can take the full benefit of it. Again, find your trade-offs. In all kind of optimization, you're gonna sacrifice something, but can you sacrifice something so that the outcome is something that you can still live with? Identify that. Don't use someone else's trade-off, because their objective might be different than yours. And then after that, apply some techniques to reduce all the details, because as long as it's fulfill your constraint, then you should be able to live with it. And then use some form of encoder that does exhaustive work, so that everyone can benefit from that compression, while you need to do this only one time. Again, the technique, just to summarize, we have that and we tried to reduce the file size and the quality just a little bit, so nobody noticed that. This is the sacrifice the details part. By sacrificing some details, hopefully you can also reduce the file size. And then we use the exhaustive encoder to preserve all the details, preserve the quality, while spending a lot of time searching for the best possible optimization so that the file size continue to decrease. For more resources, I highly recommend reading these 3 books: High Performance Images from Akama and Fox, Designing for Performance from Lara Hogan. Understanding Compression is one of the best books about compression if you're afraid of math, or you don't want to know about the details about certain scary things about compression. I highly recommend reading the book from Colt and Alex. So you can find the slide deck on speakerdeck.com/Ariya. And if you like this talk, follow me on Twitter. If not, just follow Uber or someone else. Thank you very much.